the electron configuration for atoms, and we did for some d block elements that were the exceptions to following the offer principle. Here comes the electron configuration of ions. For now, just remember that for positive ions, whenever you see positive, just subtract the electrons, okay? And when you see negative ions, you add electrons. And why are you doing that? Because positive stands for protons, and there are more protons when there are less electrons. So that is why you are showing subtraction of electrons from parent atom. And when you see minus charge, negative ion, just add electrons. And why are you doing that? Because negative stands for electrons, and there will be more electrons if you are adding more electrons. So plus stands for protons and minus stands for electrons. When you see positive, you subtract electrons. When you see the negative sign, you add electrons. So here for, let's say, sodium ion, when you look at the periodic table, look at the parent atom. For sodium ion, you have 11 electrons for parent atom. However, it says Na+. So what did we just learn? That when you see positive ions, it means electrons are lost. How many electrons are lost here? 1. So it is 1 electron lost. So the parent atom for sodium has 11 electron. So if the 1 electron is lost, that means you are going to write electron configuration for 10 electrons. So 1s2, 2s2, 2p6. So once you have written this adds up to 10 electrons, right? That's what it is, sodium ion here. And then that is my neon. That's our neon. Neon has 10 electrons. So what is happening here? By losing 1 electron, sodium became isoelectronic with neon. So these are this ion and this atom, they are isoelectronic. Iso means same, and what is same here? The same electron configuration. So ion has, this ion has completed its octet. See this, 2 plus 6, 8 electrons, just like the nearest noble gas, which is neon in this case. So they have identical electron configuration. All right. So when you have to write electron configuration of ions, just look at the charge. Is it plus or minus? Then you look at the parent atom. How many electrons are there in parent atom? If it is plus, how many pluses? Then you subtract. If you see minus, how many negatives? Then you add as many negative charges you see. You add those electrons to the electrons in parent atom. Okay, let's do example of negative ion. So here my parent atom is sulfur, and you look at sulfur. This is sulfur here. Sulfur has 16 electrons, right? So 16, and it says 2 negative. It means there are 2 electrons added, because negative stands for electrons. So 2 extra electrons. So I have 16 plus 2, 18, and it becomes argon. So here you go. It is 18 electrons. So when you write electron configuration, remember we are following the sequence. Don't forget that. Follow the sequence from here until you have 18 electrons, or you can follow this chart, and you are following the 3 principles. And you remember that S can have maximum 2, P can have maximum 6, and T can have maximum 10 electrons, and F can have maximum 14. Everything is same, except the number of electrons will be different from the parent atom. That's the only difference for ions. 1s2, 2s2, 2p6, 3s2, 3p6. So what is happening here? 10, 12, 6, 18, which is argon. So argon, Ar, and this one is S2 minus. So what are these? Sulfide ion is isoelectronic with argon. Okay. So why did this gain 2 electrons? Because it attains the no electron configuration of nearest noble gas to complete the octet, to be more stable, to be less energetic. This is the last shell. 2 plus 6 is 8. So if you understood this, your turn. Please complete this chart. Complete the chart, pause my video, and if this is what you got, that means you have it, you got it. Since it is 2 plus ions, 2 plus meaning the parent atom magnesium has lost 2 electrons and it became ion. Here it is 1 plus, so 1 lost, 2 plus means 2 electrons lost, 3 negative means 3 electrons gained, it is 3G, 3 gain, 2 minus means 2 electrons gained, so 2 gain, 2G. Now the parent atom, this is an ion. Magnesium parent atom has 12 and it lost 2 electrons, so 12 minus 2 is 10. Potassium, the parent atom has 18. So how do I know this? I'm looking at the periodic table. Periodic table will tell you how many electrons are there in the parent atom. Potassium has 19, it lost 1 and it is now 18. So ion of potassium has 18 electrons. Strontium or strontium, it has 38 electrons. And the ion, how did it become 2 plus ion? By losing 2 electrons. So it is 36 electrons for strontium ion. Phosphide ion, parent phosphorus has 15 electrons. It has gained 3 electrons. Now it is 18 electrons in total by gaining 3. Similarly for oxide ion, the base atom is, the parent atom is oxygen, which is 8 electrons. 2 electrons are added, 8 plus 2 is 10. So, and why did it all happen? Why does it matter? Why would they lose or gain? To obtain the same configuration as nearest noble gas. So you will be writing electron configuration of all these ions. So please practice writing electron configuration of all these ions. Here I have just shown you the number of electrons in these ions, and I have shown you which noble gases they are isoelectronic with. So please try on a separate piece of paper, write electron configuration for magnesium ion. So you're writing electron configuration for 10 electrons, potassium ion for 18 electrons, strontium ion for 36 electrons, phosphide ion for 18, and oxide ion for 10 electrons. Okay guys, here let me do one exception. So what happens is there are some elements, some ions. So actually we are working on ions, okay? Since we are working on ions, we are going to focus only on ions. So ions of transition metals, some of them, they are still stable. They are stable even with the incomplete octet. All right. And here, the thing is with the metals, the other ones, when you were doing your examples like for sulfide, I didn't ask you to write for the parent atom first. I didn't ask you to write the electron configuration for parent atom. I just told you to write electron configuration for ion. However, when you're working with these exceptions, it is advisable that you write down the electron configuration of the parent atom first. And there is a reason. So let me explain it to you. Why should you write down the electron configuration for parent atom first, and where can be the confusion? Okay. Common example, iron. Look at the periodic table. Iron has 26 electrons. And the common ions for iron are Fe2 plus and Fe3 plus. These are the two common ions. So these are both are stable. So first I will say, please write the electron configuration for iron. You are going to follow the sequence here, and you are going to add electrons starting from here until you reach 26, because there are 26 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. When you add them, it is 26. When you draw the orbital diagram, this here, this is p orbital. So for the p, you make 3 orbitals. S, you make only 1 orbital. This is again p, so you are going to make 3 orbitals. And this S, you make 1 orbital. For D, you make 5 orbitals. right? Here you go. Now you put electrons, 2 electrons, 1 and 2, 2 electrons again, 1 and 2, 6 electrons, 1, 2, 3, 4, 5, 6. Here it is 2, 1 and 2, 6, 1, 2, 3, 4, 5, 6. Here 2, and this one is 6, 1, 2, 3, 4, 5, and then 6, right? Okay, now if you have to write, just for the sake of simplicity, I'm going to write the noble gas notation. So 2, 2, 6, 10, 12, 18. Okay, so 18 is argon. Instead of all this, I'm going to write argon. And I'm going to leave this 4s2 and, sorry, 3d6 and 4s2. Actually, I could write either way. So it could be 3d6, 4s2 or 4s2, 3d6. For now, just because I wrote this first, I'm going to write 4s2, 3d6. Now, why did I ask you to write the parent first? So for iron 2 plus, it means it has lost 2 electrons. Fe2 plus means 2 electrons lost. Okay? And 3 plus means 3 electrons are lost. 2 plus means 2 electrons are lost. So here it was 26 for the neutral atom. For Fe2 plus, it will be 24 electrons. Okay? Now, where am I? So, which one is going to lose the electron first? You might think that you have to lose electrons from 3D. But no, you lose electrons from 4s level. And that is why you need to write the electron configuration when dealing with these exceptions. So, it will be for iron Fe2 plus, it will be Ar. This 4s will become 0, no electrons, so we don't even need to write this. So we will have this one. Okay, so look here. This is the electron configuration for Fe2 plus. Okay, why am I writing 10? I'm so sorry, guys. It is 6 here, not 10. My apologies, sorry. 6 electrons. That was my mistake. I was looking at the maximum number of electrons. So 3d6. So that's for the Fe2 plus. Now for Fe3 plus, that means it has lost 3 electrons. So if it is losing 3 electrons from 26, it will be 23 electrons now. Now you have to write for this one. You again look at the parent. Parent is Ar. But you have to lose 3 electrons. So you're not going to lose from here. You're going to lose 2 from here and 1 from here. And you are going to get 3d5. Okay? This goes back to the rule of half-filled d orbitals and completely filled d orbitals. So here you can see this here. 3d5 is it's half-filled d orbital. Maximum electrons in d can be 10. So 5 is completely half-filled. So this 3 plus is actually more stable than 2 plus, but still these both are stable ions of iron, Fe2 plus and Fe3 plus. So I want you to practice, guys. I hope this makes sense. Thank you, and practice as much as you can. Thank you.